Hello, AP Chem students, and welcome to topic 9.7, coupled reactions. The learning objective for today is 9.7.a, explain the relationship between external sources of energy or coupled reactions and their ability to drive a thermodynamically unfavorable reaction. So there are unfavorable reactions thermodynamically that do still occur in nature, and they need to happen. So how can we make that work? So they can be made to work with either a provided energy source, so some kind of external energy source, such as the sun, or by plugging it in, or they can be coupled to a thermodynamically favorable reaction and happen kind of like in a waterfall effect. So there's a couple of common examples that I want to point out. So first of all, with an external energy source, we plug in a cell phone to charge a battery or any other rechargeable battery. We also use the sun as an external energy source for the light cycle in photosynthesis. In terms of coupling it to another reaction, we couple the conversion of ATP to ADP. We'll look at that again in just a minute. And then the dark cycle in photosynthesis is coupled to the light cycle in photosynthesis. And that's how photosynthesis is a cycle that can happen all the time. So this is ultimately, of course, related to free energy. So if we substitute the equilibrium expression for K in the relationship between K and delta G, you can see that delta G is equal to negative RT natural log of the concentration of products over the concentration of reactants. And again, I'm not telling you anything new here. I'm just showing you how relationships that we already know to be true interweave together. So it makes sense that the free energy, which must be negative in order for the reaction to proceed, depends on the concentrations of the reactants and products and their coefficients. And so what happens a lot of times when we drive a thermodynamically unfavorable reaction by coupling it is we couple it with an intermediate. And so sometimes you can see that we can increase the concentration by having two reactions that feed into the same species, that produce the same species, for example, and then that might change my delta G by changing the concentration. So that's one way this can occur. But I liked this graphic, and so I wanted to blow it up for you and show that in this case, if your delta G is less than 0 and your Q is less than K, then your reaction will naturally proceed until the point at which your K is equal to your Q and your delta G is equal to 0. Then, on the other hand, if you've got this situation where your Q is greater than K, of course, we go in the reverse reaction, okay? And so, there is a point at which this happens. And so this graph is showing you percentages when this would occur under these conditions. And I don't care about that as much right now, but we can shift these percentages by changing the amounts here by coupling it to another reaction. So remember the application of Hess's law to Gibbs free energy. We said that the overall free energy change for the coupled reaction would be equal to the sum of the free energies for those combined reactions. So just like we did with enthalpy, we can sum to give free energies for reactions that sum to give an overall larger reaction. So therefore, a thermodynamically unfavorable reaction can be driven by being coupled to a thermodynamically favored reaction. And then again, as I said a second ago, the coupling can occur via a common intermediate. So if we look here, the term exergonic and endergonic is used in biology, but it really just means exothermic and endothermic. So you can have reactants or produce products, and then on this way, and then the other way it goes like this. And so what we can see with the conversion of glucose in the cycle of ATP to ADP is the glucose to carbon dioxide, water, and heat is an exothermic reaction that drives this conversion of ADP to ATP. And then as ATP converts back to ADP, then that is an endothermic reaction, and amino acids convert to polypeptides, that peptide bond formation. And then this is a cycle that just goes and goes and goes. And you'll learn more about this in AP biology or future biology classes. But this is a really common example of coupled reactions. Okay, so that's actually it for this topic. So what should you be able to do with this? We should be able to describe how two reactions can be coupled to make a thermodynamically favorable process occur, recognizing that summing the Gibbs free energies will be a very clear way to show that that can happen, and also that they often happen through the formation of a common intermediate. Now, we are going to look more at the external energy source as we proceed with the rest of Unit 9, because we are shifting now from talking about all systems in thermodynamics, and we're going to focus on specific cases of electrochemical cells. And so we'll be starting that in the next topic, and I'll see you then.